Okay, we're going to look at some limit comparison test examples. And we're going to start the morning with a question that looks like this. Some square root of n over n minus 1. Okay. So remember, we have to write another series, and we're going to adjust this because it doesn't look right. Here we go. This is going to be starting at 2. Okay. And so now we have a series that's defined because you can't divide by 1, so you can't start by 1. Anyway, this is a series of positive terms, and we need to create another series that it behaves like. So what we're going to do here is we're going to focus on removing the constant term. And we are left with the square root of n over n, which is simply going to be using some algebra. One over the square root of n right here. So you guys are using properties here of algebra. Which is n to the minus 1/2. And we know that this particular series is 1 over n to the 1/2. So let's remember, this is a P series here. Okay, so the power here is 1/2. And it's a P series, but it's a divergent P series, if you recall. So we have a divergent P series because the value of P here is equal to 1/2. In order for P to be convergent, it has to be bigger than 1. Right? So this is a divergent P series. Okay, so we're going to call this here the AN, and I'm going to call this here BN. I mean, it's the same thing that we have here. That's our BN. So we're going to use the limit comparison test. So we're going to look at the limit of the ratio of AN over BN, which is the limit of, say, the square root of n over n minus 1 over 1 over the square root of n. So we're going to take that product, square root of n minus 1, and we end up here with n over n minus 1. So as n gets big, this is a calculus 1 question, make it the limit of 1 over 1 minus 1 over n, and we find that this is 1 over 1 minus 0, or simply 1 over 1. So here we go. This is the value C in the limit comparison test. So by the limit comparison test, and this is what we typically say, by limit comparison test, I abbreviate it, LCT. So by the limit comparison test, we know that this particular series diverges because it's compared to a divergent P series right here. So they both diverge, and that's the limit comparison test. They're either going to both converge or both diverge. So it's completely based on what happens with the series you compare it to. If it's a convergent series, well, and you can show that the limit, and that's an and, you show that limit is finite, then they will both converge. If the comparison is a divergent series and you show that limit is finite, it's going to be positive, right? Finite and positive. By the limit comparison test, they both will diverge. So that's the essence of this particular test. And we'll look at another example. One over the cube root of 3 into the fourth plus 1. Start with 1 to infinity. Now, I'm going to find a series that this behaves like here. And you say, okay, are we going to get rid of the constant term? And the answer is yes. So when we do that, this goes to 1 to infinity, 1 over the cube root of 3n to the fourth power. And so we're going to do a little bit of algebra with this. And we say, okay, then I guess this is 1 over the cube root of 3, that constant, the cube root of n to the fourth, and this becomes 1 over cube root of 3, n to the 4/3. So here's this series. Sum 1 to infinity, 1 over cube root of 3, n to the 4/3. I can pull out the constant, 1 over cube root of 3, sum 1 over n to the 4/3 from 1 to infinity. So we're really going to compare it to this series here. And we know that this is a convergent P series. And you say, well, how do we know? Because the value for P here is 4/3, right? So P is 4/3, and that certainly is bigger than 1. So we're going to compare it to a convergent P series. So if our limit is going to be positive and finite, then they both will converge. So we're going to call this AN, and we're going to call this particular series over here BN, which is the same series all the way through. Okay, the whole thing there. And let's start looking at this limit comparison test. So here we go. The limit of AN over BN becomes the limit of 1 over the cube root of 3n to the fourth over 1. Oops, don't forget we have to add 1 there. Plus 1 over 1 over the cube root of 3n to the fourth. And that's the limit of 1 over the cube root of 3n to the fourth plus 1 times the cube root of 3n to the fourth, which is the limit of cube root of 3n to the fourth over cube root of 3n to the fourth plus 1. Now, by properties of radicals, this is the limit of the quotient, 3n to the fourth over 3n to the fourth plus 1. So you can actually use your property here for saying this is the cube root of the limit 3n to the fourth over 3n to the fourth plus 1. N gets big, and this now becomes a calculus 1 question, meaning divide every term by n to the fourth. And you end up with cube root of limit 3 over 3 plus 1 over n to the fourth, right? And goes to infinity. So this is going to be the cube root now of, remember, this portion actually goes to 0. So you get 3, we'll say 3 over 3 plus 0. And you really end up with the cube root here of, 3 over 3, which is 1, which is 1 again. That's the constant. So we got a finite limit. And when the limit is finite, by the limit comparison test, that's what we're going to say, by the limit comparison test, we have an answer for this particular, I guess we write it up here. By the limit comparison test, we know the series here converges because it was comparable to, we compared it to a convergent P series. We know that. So that's kind of how we answer the question. Okay, so by the limit comparison test, this converges. So we got some extra examples here this morning for you guys. And let's look at something like this. Not too hard. 1 over 2m plus 3. Okay, we're going to have to determine a series that it behaves like. And again, what you want to do is remove the constant term. And now you get 1 over 2 to the n. And I can factor out the 1/2 and then get 1 over n. And then this is a divergent series. And you say, how do we know it's divergent? Well, it's the famous harmonic series. The harmonic series diverges. We proved that earlier. So, okay. This is going to be our AN, and this is our BN. We're going to look at the limit here of the ratio of AN to BN, which is the limit of 1 over 2m plus 3 over 1 over 2n. And this will give you the limit of 1 over 2m plus 3 times 2n, which is the limit of 2n over 2n plus 3. Now, again, from Calculus 1, we're going to divide every term by the variable with the highest power in the denominator, which is n, n, n. So you get the limit here now of 2 over 2 plus 3 over n. And remember, this is as n gets big. So as n gets big, this portion goes to 0. And you're going to end up with 2 over 2 plus 0, or again, 2 over 2, which is 1. And that's your constant there, C. So we're going to say now, by the limit comparison test, this series diverges because it's compared to, they both diverge, it's compared to the famous divergent harmonic series. And that limit there, remember, is a constant value. So these are the examples that we did, or some more examples that we were working on in class here. And let's take a look at another. We're going to kind of kick these up a little bit. N plus 6 over n over, I believe that's 4 over n, n plus 6 to the n power here. Now, this is kind of interesting. It's a bit interesting because of the fact that you might say we have to find a series that this behaves like, and we don't have constant terms. And you're right, we don't have constant terms, but I want to remind you here, here's kind of the idea of what we're doing. We're trying to remove the less dominating terms, the terms that are less dominant. And the terms that are less dominant are usually the constant terms, right? Well, comparing these two terms to, let's say, um, n and then 6 to the n, or even up on the bottom, it's the same kind of thing, n and 4 to the n. The exponential terms dominate the series because exponentials, like if you say 6 to the first, 6 to the second, 6 to the third, 6 to the fourth, or even 4 to the first, 4 to the second, right? Those answers or those values, since they're exponential, they get big really fast, comparable to the n's. So in this example here, because n just, gets big in a linear way, and the exponentials get big in an exponential way, and there's nothing faster than exponential growth. So the less dominant terms here are the n's. So you're going to remove the less dominant terms. And so that series that you compare it to will be now 4 to the n over 6 to the n, and that's what you're going to look at. And so you say to me, okay, well, what kind of series is this? Using a little bit of algebra, this is 4 6 to the n, which really becomes 2/3 to the nth power. And what you're seeing here now is a geometric series, where r here is 2/3, and we know the absolute value of r is 2/3, which is strictly smaller than 1. And this is a convergent geometric series. So this converges. So we're going to compare it to a convergent geometric series by the limit comparison test. And so we know this is our AN and this is our BN. So now the limit here of the ratio AN to BN is a limit of, now you say, well, what's AN? It is n plus 4 to the n over n plus 6 to the n divided by 4 to the n over 6 to the n. So remember, you have a complex fraction, n plus 4 to the n over n plus 6 to the n times 6 to the n over 4 to the n. Okay, so we're going to use a little algebra here. We're gonna multiply to our numerator, multiply to the denominator. This gives us n 6 to the n times 4n times 6 to the n over n times 4 to the n plus 6 to the n times 4 to the n. And now we get n 6 to the n. I think there's a plus there. Yeah, there's a plus there. And using properties, that's 24 to the n now, right? We're going to multiply these two. Same thing down here. So you get n here, 4 to the n, plus 24 to the nth power here. Okay. Yeah, let's see if we can make this a little bit clearer, a little bit nicer. Now, here's the thing. The question is, what's this limit? And you kind of have a problem here. We're gonna approach this in the same way because you're going to have a bunch of infinity over infinity because n gets big, right? You're going to have this situation, and you can, in theory, um, write this question in terms of real variable x, and then possibly take L'Hopital's rule. And I think if you do that, you might end up with some work that might require heavy algebra. Now, here's what I'm going to say to you. Here's what we're going to do. What we're going to do here is we're going to use the same tact, same approach that we did before with the calculus setting, meaning we're going to divide every term with that 24 to the nth power here. So every term, 24 to the n, 24 to the n, 24 to the n, and then 24 to the nth power. And what you get here is that limit, n goes to infinity, will be, let's write this down, n times, I guess we have to do every detail. Well, we don't have to do every detail, right? We can say n over n over 4 to the n plus 1 over n over 6 to the n plus 1. We're going to look at this as n gets big. And so here's what's going to be the question. Let's note here. By properties of limits, what you guys are going to get is the following. You have the limit n over, n over 4 to the n, plus that limit of 1 over the limit of n over 6 to the n, plus that limit of a constant 1. I typically don't write that down for you guys. I just say properties, but I want to show you here some detail. And then the question is, what's going on here with these particular limits here? Right? So you're going to have to find some of these limit values. Now, if you guys, I guess we could go to those kind of details here. So let's go to show you a few things. So I want you to note, you have the limit of n over 4 to the n. And you say, as n gets big, we know this is infinity over infinity. Okay, so it's infinity over infinity. Okay. Well, then, looking over a few things, some questions here. Then here, you say to ourselves, well, what do we do with this? Right? What you're going to do is you can convert this to calculus. And you say, do I have to, now we're going to look at this as the limit, and I'm going to change some colors here. Let's go to blue, I guess. What's the limit as x gets big? X over 4 to the x. Well, that limit here, by L'Hopital's rule, is the limit of x gets big. Remember, differentiate the numerator and differentiate the denominator. And that's going to be the limit here. This is by L'Hopital's rule of 1 over. Now you have to remember, what's this derivative here of 4 to the x? Well, it's 4 to the x here times the natural log of 4, and that's a constant. And this is as x gets big. The point I'm making is that this limit is actually 0. And you can kind of sense that happening because of the fact that, and that means here, ladies and gentlemen, that this limit is 0, by the way. And you could kind of sense that happening already because of the fact that here, your numerator is linear, but the denominator is exponential. And what that means is that ratio of the two is going to go to 0 because the denominator is going to increase much, much faster than your numerator. So you knew that coming in just by looking at that. And so you don't have to necessarily use L'Hopital's rule. If you can see that, that's fine. We know that limit goes to 0. And so I want to point that out to you that, if you're going to apply L'Hopital's rule, right, you need a function of a real variable. This has to be in terms of x, not n. We now go back and talk about n. And, it's a technical kind of thing. This is applying L'Hopital's rule, right? Because you have to have a continuous function and not look at these discrete values. So this is 0 here, which makes us, the point is 0 plus 1, 0 plus 1. That limit is 1. It's finite. That's the c value. So you can now say by the limit comparison test, this series converges. By limit comparison test, we have convergence. And that's what you're doing. Anyway, pretty good example. Now let's do a few more. Questions that are similar here. How about something like this? Yeah, we're going to say, how about n squared minus 5 to the nth power over n cubed plus n plus 1. Okay. So we kind of kick some of this up a bit to let you know. We're removing, like we did in the last example, we're removing the less dominant terms. And so we know for certain a constant's not dominant. And we looked at even eliminating the linear variable. So I'm going to eliminate these terms here because n squared and n cubed are more dominating here. And so be careful here. Don't eliminate everything. Eliminate, the constant terms and a linear term. And now we can see we get this by some algebra. We get the infamous harmonic series. And this is the harmonic series that diverges. So this is what we're going to use to compare. So this will be my AN, and this will be my BN. So let's use the limit comparison test. Let's get rid of the portion here. And so let's look at the limit of the ratio, AN over BN. And just doing a little algebra here, we end up with n cubed minus 5n squared over n cubed plus n plus 1. And now we're going to do the same things. This is a calculus 1 question. Divide by the variable with the highest power in the denominator. N cubed, n cube, n cube, n cube. Limit 1 minus 5 over n over 1 plus 1 over n squared plus 1 over n cubed. We're going to look at this limit. This portion here goes to 0, goes to 0, goes to 0, and we end up with 1 minus 0 over 1 plus 0 plus 0, which will be 1 over 1. And again, that constant is 1. It's positive. It's finite. So by the limit comparison test, we have divergence. Now you say, why divergence? Because the harmonic series diverges, and the limit comparison test says they will both diverge because of the fact that we showed that the limit here is finite and positive. So if we go back to, remember, this is what you guys are doing here. Let's go back to, we started with comparison, and this is the limit comparison test, right? This was our theorem that we work with. Where is it? I think I proved it there, yeah. That was the proof. Here's the theorem. So this is from our notes. This is what we're doing, the limit comparison test. So they both either both converge or both diverge if we can show that this limit is finite. That's what we're showing. All right, so another good example. Yeah, I guess we could try one more. Well, they look kind of similar. Yeah, how about, I mean, I could do similar ones. I think I want to do some dissimilar. Sum e1 over n to the n, and n is infinity. Anyway, well, this one really seems like, what do we remove, right? We're going to look at this series and we say, what exactly do we remove here? Well, the limit comparison test, ladies and gentlemen, if you notice, it just requires you to compare with a positive term series. So really, any series that has positive terms can be used. But we have to show that the limit is finite, you know. So what I'm going to do here is, if I start talking about what do we kind of remove here, well, you know, I'm going to compare this to 1 over n. And you might say, well, you got rid of the constant to a power. I did. I mean, that constant e to the power, the power n, as n gets big, 1 over n goes to 0. So that constant is really going to 0. Sorry, 1, because it's e to the 0. So I'm leaving the nth term, but like I said, I'm going to get rid of that e to the 1 over n, but I can compare it to, I could use any positive. I could even use something like this. I can say, 1 over, I can use an n squared. I can compare it to any positive term or any positive series that has positive terms, because that's what the theorem says. It doesn't say anything specific about these. So, just to kind of remark about that, just to let you guys know. But anyway, we're going to compare it. And we know, again, that this, by the way, is the infamous harmonic series, and that harmonic series diverges. So it's harmonic, and it diverges. So let's go through the comparison here. So let's see how this works. AN, BN. Let's look at that limit. The limit of the ratio of AN over BN is the limit of e to the 1 over n divided by 1 over n. Which is the limit of e to the 1 over n times n, which really is the limit of e to the 1 over n. So I was able to get rid of that term. And so what we know here is as n gets big, 1 over n goes to 0, which means e to the 1 over n goes to e to the 0, which equals 1. Again, this is finite. That's the c. So this is finite, and since the comparison series diverges, so in fact does the original question. It diverges. Anyway, that's kind of an interesting, different example. So let's do another kind of interesting example. Things that are a bit different. So you get a good idea about this limit comparison test. What if they give you sum 1 over n to the 1 plus 1 over n power? Let's write this down. Okay. So let's find a series that this behaves like. Now, because I have a bunch of constants, I kind of like that, because if I said to you, I'm going to actually do what? If I get rid of some constants here, I mean, I could compare it to something like this. 1 over n to the 1 over n, but then I don't know anything about convergence for that. Right? What is that? I don't know how that converges. I'm not sure. I might have to use a comparison for the comparison. And if I said to you, well, use a comparison for the comparison, well, if I get rid of this term, I get the harmonic series. So why don't I just do that to begin with, right? So if I said, well, how am I going to compare? If I start comparing 3, no, let's just start by, right, if we got rid of that term, we get this positive term. Let's just start with this term here, the harmonic series. So we're going to do that. Now we know it diverges. So here's our AN, and then here's going to be our BN. So we're going to look at the limit of the ratio. So that's the limit of 1 over n to the 1 plus 1 over n divided by 1 over n, which here is going to be the limit of n over n to the 1 plus 1 over n. Now, let's do some more algebra. N to the 1 times n to the 1 over n, right? Because this is a sum here. And these are properties of exponents. And this actually cancels. So we got cancellation here. So we're going to get the limit now of 1 over n to the 1 over n. Now, we don't know what that limit is, because if we try to apply this, what do we get? This is a bit interesting, right? So we have the numerator is 1, and then we have the denominator. We're not sure. That looks like infinity to the 0 power, right? Because remember, if I try to look at I could look at it this way. It's limit of a constant over the limit of n over 1 over n, and we know we get 1 over, this is an indeterminate power here, right? So down here is the issue we're talking about. What is that? So in order to answer that question, we're going to have to go out to calculus and say, okay, we need the limit now of x to the 1 over x power as x gets big. So we have to think about that situation, because this situation is infinity to the 0 power. It's an indeterminate power. So if we work with L'Hopital's rule, right, we say y is going to be x to the 1 over x, which means natural log y is natural log of x to the 1 over x, which really is 1 over x natural log x, which is natural log x over x. And as x gets big, we get infinity over infinity. We can now apply L'Hopital's rule. So by L'Hopital's rule, this is going to be, let's be careful here, right? I want to be careful with our notation here. Be very careful. I want to say this is natural log y is really natural log x over x. So notation-wise, I'm saying as x gets big, yeah, we get this infinity over infinity because we're applying the limit, okay? And so the limit now of natural log x over x by L'Hopital's rule is 1 over x over 1, which is the limit of 1 over x as x gets big, and that limit equals 0. And so what we showed here is that as x gets big, we showed natural log of y goes to 0, which we're showing really e to the natural log y goes to e to the 0, or we're really showing that y goes to 1. And that's what we're looking for here. So the bottom limit, this limit is really equal to 1, which means for our sequence that this portion here is 1. So we have really 1 over 1, which we know as 1, and that's your constant, that's your c in the limit comparison test, right? It's finite. So we say by the limit comparison test, we have divergence. Right here. By limit comparison test, we have divergence. There we go. So that's kind of an interesting kind of question here today. Anyway, looking over some more. I don't know. Let's try to do maybe one more, a few more, see how this goes. 1 over n square root n squared minus 1. We want to see what this series behaves like. Oh, we got some nice constant here. And will that give us a series that we can work with, we could recognize? Right, let's make sure I wrote it down, okay? That's by some algebra. And this is a convergent P series. because we have the value of P being 2. Convergent P series. So we're going to have to find here AN and BN. Right? It's really your BN. It doesn't matter which one you use. So the limit AN over BN becomes that limit of, and AN is 1 over N square root N squared minus 1 over N squared, which is limit of 1 over N square root N squared minus 1 times N squared, which is the limit here of N over square root of N squared minus 1. Okay. So then the question is going to become here, I'm going to write it down a bit nicer. Here's going to be the question. You know, you kind of seen something like this in, in Calculus 1. These kind of limits. Now, remember something here. I could do a few things here with this. I'm going to replace this N here. All right. I'm going to say square root of N squared. I can do that because N is positive, right? So the square root of N squared will be N. It's really the absolute value of N. And I'm going to try this way because it's always good to see how to do things differently. And you may say, well, what does that do for us? Well, I'm going to use properties of radicals, put this under a single radical, right? And then that gives you a square root here of the limit. N gets big, N squared over N squared minus 1. We're going to divide by the variable with the highest power in the denominator. We're doing a Calculus 1 approach. N squared, N squared, N squared. And so this gives us square root of the limit of 1 over 1 minus 1 over N squared. And that means this portion here goes to 0, which means we have the square root of 1 over 1 minus 0, or the square root of 1 over 1, which is the square root of 1. Again, here's a nice finite value. Your constant, it's finite. That's what we need. And what that would say for us is that both series are going to be convergent. So we say, by the limit comparison test, we have convergence. Because we showed that that limit was actually finite. So, ladies and gentlemen, here's a good example. And let's see if we have time for another. No, I think we're going to call it a day. All right. So this morning I did want to give you guys some extra examples, and I did. So you got about 50 minutes approximately of some examples. I will upload this to the website and inform you and put it in Canvas. And I hope you guys have a nice day. And like I said, I got some extra examples for you guys.